All right, welcome to This Explainer. Today, we're tackling something that, let's be honest, gets a bit of a bad rap, but is actually one of the absolute most powerful analytical tools we have. We're talking about algebra. We are going to take all those floating, abstract letters and turn them into highly tangible, real-world concepts. By the end of this, you won't just be memorizing formulas, you'll literally be able to see them.
Okay, so let's just address the elephant in the room right off the bat. Why on earth do we suddenly start mixing the alphabet into our math problems? For so many of us, the second an X or a Y shows up next to a number, panic just kind of sets in, right? It feels intimidating. But here's the secret. We're not actually trying to make math harder. We're using letters to create a universal template. Variables are really just placeholders for the physical world, and they allow us to generalize solutions for literally any situation.
So here is our roadmap for today. We'll learn the language of algebra, size up expressions, tackle operations, and look at some core identities. Then we'll visually prove these concepts and wrap up with a real-world application. All right, let's kick things off with Section 1, the language of algebra, or as I like to call it, the grammar of math. Think of algebra not as some giant list of arbitrary rules, but as a brand new language where numbers and letters combine to make mathematical sentences. So an algebraic expression is just a mathematical phrase containing constants, variables, and operators. Think of a constant as a fixed number, like 9. It never, ever changes. A variable is a letter, like X or Y. And operators? Those are just your standard addition, subtraction, multiplication, and division. When you put them all together, you get an expression.
Let's actually break one down. Take the expression 5x plus 8y. We've got our variables, x and y. The numbers attached directly to them, the 5 and the 8, are called coefficients. And the individual building blocks, separated by that plus sign, the 5x and the 8y, those are called terms. Honestly, just getting this foundational vocabulary down makes the rest of this journey so much smoother.
Moving right along to Section 2, monomials to polynomials. This is all about sizing up expressions. We basically name these mathematical phrases based on how many terms they have. Just like prefixes in everyday English, mono means one. So a monomial is an expression with one term, like 5x squared. Bi means 2, making 5x squared plus 2y a binomial. And tri means 3, giving us our trinomial. And for the whole shebang, anything with one or more terms with non-negative integer exponents falls under the big umbrella category of a polynomial. Now, before we start playing with these terms, we absolutely have to recognize a huge common pitfall. There is a massive difference between like and unlike terms. Like terms have the exact same variables, like 2x and negative 9x. Unlike terms have totally different variables, like 24xy and 5pq. You can only add or subtract like terms together. Just like you can't combine apples and oranges, there is just no way you can combine an x with a pq.
Okay, Section 3, operations and expressions. Time to actually do the math.
When you're adding these algebraic expressions, honestly, organizing the problem visually is half the battle won. First, write the expressions in different rows. Second, and this is absolutely crucial, align the like terms in the exact same column. Finally, just add the coefficients together like you would any normal numbers. Keep it neat, and the math basically does itself.
Now, multiplying unlike terms, that takes a little bit of sequential logic so we don't trip ourselves up. Step 1, multiply the coefficients together. Step 2, keep the different variables side by side. Step 3, if some variables happen to be the same, you just add their individual powers together. So 2p times 3q, that's just 6pq. Simple as that.
Which brings us to Section 4, the core algebraic identities. Let's talk about mathematical shortcuts. I know. These standard identities are usually taught as these big, scary formulas that you just have to rote memorize for a test. But actually, scratch that. They are just incredibly useful mathematical shortcuts that will save you massive amounts of time. When you see a plus b, all in parentheses, squared, you don't have to do the long multiplication. We automatically know the shortcut is a squared plus 2ab plus b squared. Same goes for a minus b squared and a squared minus b squared. But why do these specific shortcuts exist? Why does the math always work out this perfectly? Let's find out in Section 5, Visualizing the Math, because seeing is believing, right? To really prove why those shortcuts work, let's turn those letters into physical space. Imagine A and B are just lengths on a piece of paper. If you have a square with a side length of A, Its area is a squared, represented here by this blue square. A smaller square with side length b has an area of b squared. That's the red square. We've also got two green rectangles with lengths a and breadths b, giving them each an area of ab.
Now check this out. If we literally arrange those cutout pieces, locking the a squared square, the b squared square, and our two AB rectangles together like a giant puzzle, they form one massive square. The side length of this new giant square is exactly a plus b. Therefore, its total area is a plus b squared. Look at the pieces inside. It is literally made of 1a squared, 1b squared, and 2 ab's. The visual proof perfectly matches our algebraic shortcut. Mind-blowing, right? Let's look at another one. Here we have a large square constructed on graph paper. Let's just call the length of its side a. So the entire surface area you are looking at right now is a squared.
But what if we want the identity for a squared minus b squared? Well, visually, that means taking our large a squared area and physically cutting out and removing a smaller square with area b squared from the corner. If you rearrange the remaining colored paper, it perfectly forms a brand new rectangle with a length of a plus b and a breadth of a minus b. The math is literally proving itself on paper. Finally, Section 6, Real-World Applications. Let's go build Ravi's pool. Okay, let's bring all this theory back down to earth. Meet Ravi. He's been having some health issues, fatigue, joint pain, you name it. So he decides to follow a strict diet and exercise regularly. And to do this, he's going to construct a rectangular swimming pool in his yard. This is exactly where polynomial math steps out of the textbook and solves a physical, real-world construction problem. Based on his plot of land, Ravi's pool needs very specific dimensions. The length of the pool is 2n minus 5 meters. The breadth is 2n plus 5 meters. Now, notice anything familiar about those expressions? They map absolutely perfectly to the algebraic identity we just talked about, a minus b multiplied by a plus b. And because we know our shortcut identities, we don't even have to do the complicated multiplication to figure out the pool's base area. The identity tells us that a minus b times a plus b equals a squared minus b squared. In this case, 2n squared minus 5 squared. That instantly gives us a base area of exactly 4n squared minus 25 square meters. So what does this all mean? Well, it translates to cold, hard cash. Ravi wants to tile the base of this pool, and tiling costs 15 rupees per square meter. By multiplying our polynomial base area by 15, we find the exact cost equation, 60n squared minus 375. No matter what value Ravi eventually chooses for n, he knows exactly what his budget needs to be, for sure. And guys, that right there is the true power of algebra. It's not just letters on a page, it's a way of modeling our reality, calculating costs, and building physical structures. So I want to leave you with this thought to end our explainer today. Look around your room right now. How could the dimensions of the everyday objects around you, your desk, your rug, your screen, be represented as variables and polynomials? Once you start seeing the world through the analytical lens of algebra, I promise you, it completely changes how you understand the space around you. Thanks so much for joining me, and keep exploring.